there's some methodologies that are really designed for learning parameters while being aware of the downstream decision-making procedure, right? So you'll see what I mean by this. But basically, in many optimization problems, you estimate parameters through this kind of predictive analytics, like regression, logistic regression, like classification and all this. Now, you take these parameters, learn from these ML techniques, and then you input those parameters into optimization, and you solve that optimization problem to generate decision. Now, what could be potentially problematic is that these parameters that are learned are purely based on the very specific loss function in machine learning context. And when you try to learn these parameters, that machine learning phase is not aware of how these parameters are going to be used in the future, right? Parameters are going to be used for the downstream optimization steps. But when you are too focused on that machine learning phase, right, that part is not really taken into account. And sometimes there exist multiple predictions possible, right? And what kind of parameters they want to choose to really lead to a good decision, or the decision that is actually stable and reliable, okay? And often, sometimes when you try to learn parameters using, for example, regression, you might want to sacrifice a bit in terms of like prediction loss function that can actually work very well for decision-making stages. Something like this is what I really mean by decision-aware machine learning. When you try to use machine learning for predicting parameters, can it actually be aware of the downstream decision-making phases? That's the topic I wanted to cover. Now, that's the overarching question that I like to ask, right? Do a good prediction lead to a good decision? Very important. Okay? So I like to think about clustering. We all know what clustering is. The goal of clustering is group data points into different clusters so that the data points that are in the same cluster are more similar to each other than others in the other clusters, of course. And that clustering depends on some similarity measures. And similarity measures, there are different measures like density, distribution-based clustering, centroid-based clustering, like k-means, but we typically use Euclidean distances to kind of cluster data points. Does that make sense? Now, what I like to think about is the following question, where the data points that are given are actually decisions, right? And they are the decisions that are made by some rational decision maker who might have actually solved some kind of optimization problem to generate that decision, right? You see what I can do is just collect a bunch of different data from you, and these data are all of your individual decisions. Now, when I try to cluster these decisions, should I cluster these decisions if each decision is a vector purely based on Euclidean distance, or is there something else, right? That's the question for this work. Okay, how would you cluster these decisions? My claim, or like the recent trend, is that, hey, should you just cluster these data points not based on the Euclidean distance, but based on the underlying preferences? Okay, because that's what matters, and that's what you can really bring with you for new context. Okay, it's more kind of transferable, it's more kind of portable in the sense, in a way, right? So, I like to think about this. Given these 12 data points, if you were to use k-means, how would you cluster them? These 12 data points. Well, the answer is obvious. Let's say 2 clusters. It's going to be the first 8, this guy, and it's going to be this guy, right? Euclidean distance, k-means clustering. Easy. But what if these 12 data points are actually decisions made by respective individual optimization problems? And can you cluster them based on their underlying decision preferences? That's the question. Now, what if the first 4 data points are actually made by solving an optimization problem based off of that feasible region, the square feasible region? And the next 4 data points are actually based off of that feasible region. And the last 4 data points are actually based off of that feasible region. Now, if I ask you, hey, can you cluster these 12 data points into 2 clusters based on underlying decision-making preferences? And now what I mean by decision-making preferences, well, essentially, this becomes the objective function, right? What would be the objective function of the decision maker that who gave me, for example, this decision or this decision? And can you actually cluster them based on like similarity of their underlying objective functions? Okay. Now, if you remember the inverse optimization part, there's inverse optimization happening here as well, actually, right? These 4 data points, the C vector that makes them as optimal as possible is probably this guy, or depending on what arrows mean, but maybe this guy, okay? Now let's say this is C1, right? Whereas the next 4 data points, the C vectors that can make them as optimal as possible is maybe moving towards that direction, okay? This is C2. And now the last 4 data points, I'm actually going back to C1, given that feasible region. So if I were to actually cluster these 12 data points depending on their underlying C vector, that would have made the decisions as optimal as possible, it's going to be this. Okay? And what that means is once you have these clusters, it is for these patients, or not patients, but customers, you gotta use C1 for their future decision making. For these guys that belong to this cluster, you're supposed to use C2 for predicting or prescribing their decisions in the future. Okay? So that's the high level idea of this work. Okay, there's C1 and C2. So that's the clustering solution based on the objective function coefficients that make the solutions in your optimal. So mathematically speaking, right, how do we write that problem? Each data point xk or x hat k is an observed decision from decision maker k, who approximately solves the following optimization problem. And the decision-making problem for each decision maker, we're going to call it DMPK. Okay. Now, if I assume that each decision-making problem or DMP is an LP, then I can write this problem as follows in a very compact format. DMPK right? Yes. Okay, each decision maker K solves the following LP. It's just the typical general form of LP. The catch is that, well, your constraint parameters are indexed by K, so your feasible regions will differ across different decision makers, of course. Okay? And you can make an assumption that without loss of generality, like, each AI, the row vectors of A matrix, the norm of it is 1. You can make this kind of convenient assumptions that will be helpful as we go. Now, given this DMPK, what you want to do is to cluster the decision makers. Okay, we want to group a set of decision data points, which I denote by X hat, into L clusters. And let's assume that that L is given. We know the specific number of clusters that that is desirable. Okay, and then what that means is there's going to be cluster index L that is from L to 1 to L. Okay, and the goal is to find the corresponding cost vector CL for each cluster. Okay, such that the optimality error associated with each observation is minimized under the original Ford problem or decision-making problem. So this is exactly what I mean. I can write it as in math, and that might actually be better. There's this given solution, bunch of decision data given. Okay, there's gonna be xk. K is in big K. I want to minimize the distance between the given data points and some new solutions xk, where that xk is the minimizer of the DMP for each decision maker. Okay. So what am I doing? So I am, well, basically assigning decision maker K to cluster L by tying them with the cluster specific CL. So what I'm saying is I believe that decision maker K, his or her preference is actually captured by this CL. There are going to be different decision makers that belong to the same cluster who are supposed to share the same C vector CL. Okay? And if I were to use the C vector, CL vector for the decision maker, then XK is going to be the minimizer. And at the end of the day, the way they want to cluster these data points or the decision makers is by minimizing the distance between the given solution and the actual minimizers that are achievable by the cluster-specific C vectors. Okay? And of course, each CL vector is in some normalization set C. It's the same requirement. Right? For example, right? C such that L1 norm is 1, something like that. Yeah. We don't know what CL should be yet. Okay, so good question. So my XK is a decision variable, but also CL is a decision variable. I'm trying to find all of them simultaneously, right? For each K and each L. That can happen, right? That's another stability issue that might actually faced by this approach, right? By adding more data points, your CL might change. Is that what you're asking about? Yeah, we assume that the data points are given and we know exactly where they are, and we could just cluster them, right? And the sequel to that, this version is gonna be the stability issue. Hey, what if like you add outliers, there's some measurement errors in the data, your CL might actually become too unstable, then what's gonna happen? That's kind of, yeah, the next stage. Okay, good question. Okay, so X is your decision variable, C is your decision variable, and the set of data that belong to the same cluster L, that's GL. And if you think about it, GL itself is going to be a decision variable. The cluster itself is going to be a decision variable. So here, I'm kind of abusing this notation, but I'm supposed to actually enumerate all X and C and G over all indices, but you know what I'm talking about, right? So this version, again, written in a very compact format, but if you think about it, there's a lot going on in this formulation. There's this combinatorial nature again, right? You're assigning different data points into different clusters, right? So GL is your variable. Then you find a CL, then you solve the DMP problem to find the minimizer, and you measure the distance to be minimized and all that, right? So very complex problem, in fact. Yeah, sure. Given data points, be feasible to every system? They need not be feasible actually, right? They can actually be outside of the feasible region, but still, right? There's gotta be some C vector that can make it as optimal as possible. Given illustrative example for yeah, right. And the reason why they're all inside the feasible region is merely for illustrative purpose, right? Good question. Okay. Okay. So with that? Right? How do we choose the distance function, right? Because we are minimizing the distance between the given data and the new data achievable by cost vectors, cluster-specific cost vectors. Okay, one way to do it is to look at the worst case distance between the given solution and the argmin set of the DMP problem when you actually use CL. Now, this also reminds you of this kind of forward stability issue, right? If you end up with a CL that leads to a wide range of optimal solutions, then probably you're screwed, right? So I want to find a C vector that minimizes such kind of variation in terms of like the optimal set of optimal solutions that is achievable by CL. So basically, this is it, right? K is the argmin in the argmin set. I wanna find the max of the distance over all the possible xk's over the argmin set. I wanna also take the max over all the clusters. And that's the one that I wanna minimize in this clustering problem. Okay? Now, that's how I formulate this problem. When the decision-making problem, this guy, is an LP. Now, if this is a convex problem, of course, you can replace everything in KKT conditions. What that means is basically, well, if DMP case are actually, I said that without explaining this, right? If all DMP problems or the decision-making problems are LPs, well, you can replace this part. You can replace the argmin part with the LP optimality conditions. Now, this goes back to how you reformulated that inverse optimization problem, dual feasibility and complementary flatness. Okay, that's these two sets of solutions will replace this part, which is right now rather abstract. Okay, so I'm gonna skip this part. Now, if the DMPs were convex, then similarly, you can replace that argmin part with the KKT conditions. Okay, that's what I wanted to say. Now, there's a theory that says that also, very much like what you observed here, when you try to cluster these 12 data points, you realize that for each cluster, the representative C vector is actually perpendicular to one of these hyperplanes. Like this. Okay? And this is actually the structure of an optimal solution for this preference-based clustering problem. And what that means is basically, if you look at this feasible region, and there are like, A1, A2, A3, and A4, there's X hat 1, X hat 2. Sorry that I'm mixing the superscript and subscripts. Okay. Okay, if I were given these 4 A vectors and 4 data points, what I can do is I can also treat this as some kind of bipartite graph. Okay, there's 4 X hats, X hat 1, 2, 3, 4, and there's 4 A's, A1, A2, A3, and A4. Okay, and now all of a sudden, this clustering problem is equivalent to covering, if this is A and this is B, set A, right? Covering set A, covering the data points with how many? L components of B. Does that make sense? You try to cluster these data points. You try to cluster these data points. And if you were to find 2 clusters, all you need is to find 2 of these AI vectors to represent sum or the partitions of the data points in a very rough sense. Okay? So what is this problem? This problem is basically an L median facility location problem. In general, we know it as P median facility location problem. Okay? And this is exactly what is happening in this setting. Okay? So what can happen is basically the following. If we define the distance between each data point and each hyperplane as like delta k, let's say f, because I use f for facet. Okay, then I can write this problem as follows. Oops, this is f. Okay. Okay. And my v and w are decision variables. Okay, so again, what that means is, well, basically, delta kf is the distance between data point k and facet f, or a1, a2, whatever that is, right? And vkf is, well, the indicator, right, where you are actually assigning data point k to a certain facet or a certain hyperplane. Okay, and what this is saying is what? You're assigning only one AI vector to data. And your V is going to be actually limited by W. And the sum of the W is going to be no greater than L. Why? Because you're finding L clusters, like you're finding L facilities. Okay? So you can only activate as many as what? L AI vectors, right? To represent the clusters. And of course, V and W are binary variables. Now, it's the typical formulation for P-median problem. It's just that L is my P. Does it make sense? Now, this is some kind of, and one way of kind of reformulating this problem. Again, it's a nice connection to a rather traditional problem. Now, the challenge in this context is, again, what like she was mentioning, as in, hey, so like you mentioned this kind of stability issues, but what about this guy? This guy is also susceptible to this kind of data noise kind of issues. And of course, right, there's more advanced like extensions of this approach where people try to address that stability kind of issues, of course. Right? And it's going to be a more complex version of p-median. Then you can ask yourself, hey, so if you were to generalize this problem to address stability, then you can also check out some literature in p-median problems to see whether there's been any attempt in p-median literature that tries to address stability, right? Given that connection. Right? This is what I would do. Anyways, why? Okay, so this drawing is supposed to be in the next slide. And I can do this. Yes. Okay, so we just exploited the very special structure of this problem to make it look simpler. Okay, and it is actually computationally faster if you solve this problem as if this was the p-median problem. And it is actually the p-median problem. Okay, and if you think about it, what we are doing here, what we're seeing here is basically the merger of the integration of clustering and inverse optimization. Do you agree? Right? You're clustering the data points, and while clustering these data points, you're kind of inferring their objective function coefficients. And inferring the objective function coefficients, what inverse optimization does. So you're basically merging clustering and inverse optimization. Then if you were to do this, or if a naive modeler were to do exactly the same task, the immediate reaction would be, well, can we just use inverse optimization individually for individual data points to get individual C vectors and then cluster the C vectors later? That could be one way of thinking about this problem. Or you can cluster the data points based on Euclidean distance proximity, right? Based on Euclidean distance, and then apply inverse optimization to different clusters post hoc, right? So what I'm claiming here, and what is actually shown theoretically, is that this integrative way of viewing and modeling this problem actually works better than this purely sequential way of clustering, okay? And that is basically consistent with the initial question that I asked you, right? Good prediction leads to good decision. Well, if you actually cluster the data points early on, like a priori, and then use inverse optimization, it'll not work as well as this integrative approach. That's the takeaway. Now, if you take a step back, you can further generalize this topic, the integration of optimization and machine learning. Okay, so let's connect back to our earlier stochastic programming setting where we have a bunch of data, right? Theta 1 and theta n, these are the observed modeling parameters. Okay, and you're going to make a decision. But now what is different in this setting is that you also observe some kind of auxiliary data that you believe have led to these parameters. Okay, so if these data parameters are uncertain parameters representing demands, travel times, then the U are the contextual data, like recent sale figures or the decision maker's specific information or the characteristics of the underlying graph, like contextual data. Okay? We have these three components, and of course, you're going to be utilizing this data in a smart way to make a decision X that optimizes or minimizes your objective function, which is f of x parameterized by the uncertain parameter data. I think I used psi in lecture 2 actually, but now it's data. Now, in general, given some distribution of data, we simply optimize over sample min. Well, you saw this, right? For example, you minimize the expected term of the C or even F. F is what I meant, right? Okay, solving SAA. What is SAA? Sample average approximation, okay? I'm trying to locate this, right? So you already have this, right? SAA in the earlier slide, so I have to write it. Now, by utilizing the contextual data, right, you can estimate data using ML. Okay, so ML-based estimation of theta is to try to basically minimize prediction error. So you use the contextual data, use ML to predict or estimate data, and then you use this data, plug that into your optimization model to generate X. And I already, at the beginning of this lecture, kind of criticized or had some doubt about this sequential approach. Remember this? Okay. So basically, what has happened traditionally is the following. You use some kind of machine learning to get this predictor, which is M of U. M of U is the prediction for the value of data given you, and then you basically enter or like plug that into your optimization problem. right? Your optimization problem initially was to minimize f of x parameterized by theta, but theta, well, in my ML-based modeling is my M of U, okay? Prediction first, then optimize. Does that make sense? Now, again, think about this question. Does a good prediction lead to a good decision? How does the primary estimation impact the downstream optimization? That's something that I'd like you to think about. Okay? So here's some example. Let's say, given the same data U, the contextual data U, you have two predictors, right? You have M1 of U and you have M2 of U. Okay, maybe one use regression and one use some other machine learning technique. So I have two different predictors. And what I like to think about is the following question, right? What if Z is the optimal objective value as a result of using this is actually greater than equal to Z star of theta and right? And what I like to think about is, well, basically, in terms of prediction error, M1 has an excellent prediction error, like, excellent L2 accuracy, for example. And M2 has a not so good prediction error. So when it comes to the pure prediction error-based performance like evaluation, M1 is better than M2. Okay? But what if we actually use these predictors in optimization? And what happens, what we see is that, well, when you actually plug M1 into your optimization problem and the optimal objective value is actually can be greater than Z hat of theta, where theta is the true parameter. Okay? Whereas if you used M2 of U, like the second predictor, and well, surprisingly, it's achieved optimal value when it's used for the optimization problem. It's exactly the same as the true parameter based objective value. Okay? You can see what's happening here. So prediction-wise, M1 is better, but when you actually used it, it's actually poor than the true optimal value, whereas M2 outperformed in terms of the optimal value or the difference from the true optimal value. And this can happen. Okay, so which one is better? Well, it depends on what you care about. But if our goal is to generate a stable, reliable decision, then you gotta choose M2 over M1. But how do we know? Okay? Now, then what that means is, can we actually, when we make a prediction, can we make the prediction, can I be aware of this kind of end goal of trying to find an optimal solution that achieves as close as possible objective function value to the true value. Okay, so that's the question. So in LP, so if you're not convinced, I have an LP example for you. It's like this. Okay, this is my C vector. Right, this is my C vector, the true C vector. Okay, and this is basically C that is based on model 2 or prediction 2, right? And this is, let's say, try to make it a bit more extreme. And this is C1 that is based on prediction 1, okay? So this is a true C vector, but you don't know what the true C vector is. But using some prediction, you have two predictors, C1 and C2. And now the purpose of predicting this is to use that for solving an optimization problem. What happens is, well, if you use C true or the true C vector, your optimal solution is supposed to be here. Okay? Now, if you use C2 vector, your optimal solution is the same optimal solution, right? But if you use C1, what happens? Your optimal solution can actually be as far as this. Okay? Just in case, I want to be a bit more precise in drawing. Okay? So in terms of decision errors, C2 is better than C1. But in terms of prediction error, C1 is better than C2, right? Because the vector is closer to the true C vector than C2 is. And that's exactly what I mean by this, right? M1, M2, how do we assess the performance of it, the performance of them? Based on prediction error, based on decision error. And I claim that it has to be decision error. And it's the recent trend of kind of optimization modeling these days. Okay? So, when did it start? 3:30? We have like 20 minutes to go. Okay. So, what we're actually supposed to be solving is this kind of contextual stochastic LP, where we make our problem, right, aware of the underlying context, and we minimize the same objective function, okay, where C is not known. So what that means is the mapping from U to C is incorporated inside this optimization problem, and our major objective is to minimize the expected value of the objective function. Does that make sense? Okay. Okay. So I don't have text here, so I'm going to be writing. But basically, the traditional goal is to find M of U such that M of U minus C is minimized. That's the goal of like traditional prediction, whereas you know, our goal, let's say, is to find a C hat that will lead to the minimized decision error. And decision error, what I mean is this, right? The gap or the difference in the objective function values, right? When you use the X that is achieved by C hat, which is your estimator, right? And you can actually assess the objective function using the true C vector. And there's going to be the true optimal, excuse me, true optimal objective value based off of the true C vector. And ultimately, our goal is to minimize that gap instead of this traditional prediction error. That's it. Okay? That's the goal. Now, traditionally, the practice of making a prediction first, then optimize based off of the prediction, we call it predict, then optimize. Okay? And then recent trend of kind of integrating the prediction and optimization towards the goal of minimizing such a decision error, people started to call it smart predict and optimize, where smart means basically integrated. Okay, so if you Google it, you'll find like quite a few papers on this topic. Very popular topic these days. Okay, so again, smart predict and optimize, I'm going to be calling it SPO. Okay, so SPO loss could actually be oftentimes ambiguous. Why? Because, hey, what if, if you solve the optimization problem with a certain C vector, again, it could be that there are infinitely many optimal solutions. If the C vector is perpendicular to one of the hyperplanes, again, infinitely many solutions that are on the same line segment will be equally optimal. So there's some kind of ambiguity in terms of assessing that gap. And that is why we have this max term, right? And again, what we do is to minimize the worst case loss in basically decision or the objective function values, right? Where in case your argument set is not a singleton, right? You look at all of them, you try to take the worst case achievable objective function value, and you assess the distance of it from the true optimal value. And that's what is called the unambiguous SPO loss. And again, because we never know what the true C vector is, we can, well, use empirical data like this. We use the empirical data like n pairs of U and C, and you can solve the empirical version, like almost kind of SAA version of this problem to approximate the true loss function. Okay? That's the overall kind of theme of this trend. Does that make sense? Any questions? Okay. Now this problem, although again I'm writing in a very compact format, it is extremely hard to solve. So there have been a lot of attempts in kind of simplifying it, and I'm just giving you one example. But one of the recent papers published in 2022, they proposed this SPO plus loss function, which is actually tractable. Right? And not only is it tractable, but it's also an upper bound for the original loss that I showed you. And more importantly, it's going to be consistent with the original loss function in the sense that if you have infinitely many data points, it'll eventually converge to the true loss function. So it's a nice paper. It's worth a read. Highly recommended. Okay. So that's an LP case of SPO, right? And there's a slightly different take on how we combine ML and optimization. Okay. Now, if you further generalize this, okay, I might have opened an older version of this. Okay. There's supposed to be F, not C, F. But anyways, right? So basically, we're looking at the same problem, but instead of an LP, we're looking at more general expression where my objective function is f of x again. My theta is still an uncertain parameter. So if you look at this problem, like contextual stochastic optimization, okay? Ideally, if you had full information for this uncertainty, then you can solve this to optimality. And full information, what I mean is the complete joint distribution of theta and u. Then you can solve this. But of course you can't, so you resort to using this empirical data, of course. Okay? Now, one way that was suggested is that smart, predict, and optimize kind of way, okay, where the goal is to minimize the decision error, okay? Another stream of research that has been quite popular is, well, actually, given a new theta, what you can do is you can search, or given a new u, right? U is the utility, not utility, the contextual data, right? And if you're faced with a new context, what you can do is to search through or over the neighborhood of that context variable and take all data that correspond to the members in that neighborhood, right? And you're gonna take all this data, right, in your optimization, right? You're in a way being a bit robust in this sense, okay? So let's say you trained your X hat using this empirical data, okay? And then there's going to be a new U here, it's given. Then what you can do is you search over the neighborhood of that U and find all the theta values that are available from the data, okay? And then only use them in your optimization by taking the weighted average. And this weight here, Wi of u, is the weight that has to be assigned to a specific data point. right, for theta I. Okay, so given you, use some kind of ML to find some nearby mu1, mu3, and mu4, and mu5, and like mu9 or 8 is a bit too far based on whatever your machine learning saying. Now, what that means is you only take these guys, okay, and there's gonna be corresponding like couple theta 1, theta 3, theta 4, and theta 5. What I'm claiming, or what is claimed in this work, the stream of work, is use these theta values in your optimization when you optimize the expected objective function value. And when you actually try to have a sum of these objective values across different theta values, maybe U1 is more similar to a new context U than U4 is, then you assign higher weight for U1, which means W1 is going to be higher than W4, something like this. Okay? So how do we identify such a neighborhood around a new context parameter? Well, one way of doing it is KNN regression. K what? Nearest neighborhood. Okay? It's pretty much like, very roughly speaking, something like this. Okay? Find me K neighborhoods or members in my neighborhood that are closest to where I am, which is a new U. And I'm going to only take the data values that correspond to them, right? And ignore all the other datas, okay? Because they are not relevant to the context that I'm specifically facing right now. So how do we find such KNN set? Well, KNN set, it is here denoted by N of U, but N of U, really, the set is defined like this, right? Immutability sin, how it is formulated, the KNN set, okay? And now you only take the objective functions for members that are covered within the KNN set, and that means the weight is going to be either 0 or 1. If that member I is inside of your KNN set, then assign 1. And other members too far probably are going to be assigned weights of 0. Okay, so this guy is going to be 1, either 1 or 0, and you're canceling all these data values that you believe are not too relevant. That's it. Okay, that's KNN way of identifying relevant data points to use for your optimization. And similarly, you can use CART, classification in regression tree. Do we know what CART is? Right. We can train, right, a model using data to make a decision tree. Okay, and decision tree like looks like this, where there's root node and there's a bunch of yes and no question to kind of branching out to different nodes. And this is how we do this. And eventually, after answering a bunch of these questions, you arrive here and it's saying, you're ISFJ. Right? That's decision tree, and that's how CART works. Okay, and instead of KNN, you can use CART in here. And what that means is you receive a new context that is you. Okay, and there's this decision tree that has already been trained to classify your U data. Then you basically plug this into your decision tree, you follow these trees, and eventually you'll be in one of the leaps, and you look at other context parameters, U1, U2, U9, U11, that belong to the same leaf, okay? And let's say my U happens to belong to that leaf, and I look around and see U1 is there, U3 is there, U9 is there, U11 is there. Hey, all of you guys belong to the same leaf. What I do is that means I'm going to take theta 1, theta 3, theta 9, theta 11. I'm going to use them in my optimization, or something like this. And what that means is, well, if you belong to the same leaf that I belong to, then I'm gonna assign 1 to the weights. If not, I'm gonna make all of them zeros. That's it. So why am I doing this? Why? Because I want to make sure that my prediction performs well in terms of decision errors, right? When I minimize this function, I want to make sure that it works well for all these predicted values. Okay, that's the interpretation basically. Okay, now that's another way of integrating optimization with ML. There's this ML way of kind of filtering predicted data to be used in my optimization to guarantee that my objective value is optimized towards like as close as possible to the true optimal value. Now, with all this, if you think about prediction, if you think about regression, there's always some measure that assesses the performance of a regression model, for example. And R squared is the most popular one, right? And what is R squared? In regression, R squared is basically what? How much of what? What's the definition of R squared? How do I perform versus the average, right? How much do I capture versus the variation that results from the simple naive average? That's what they do, right? That's what it does, right? And the reason why R2 is so popular is it's unitless and it's immediately interpretable. If it is 1, you're doing well. If it is 0, maybe your model is like nonsense. Okay? Now, well, there's an attempt in establishing this kind of performance measure, easily interpretable performance measure for this kind of predictive prescription. Okay, decision making done with prediction integrated in it. Right. So one example of it or the recent attempts is the following, which is called coefficient of prescriptiveness. Okay. So what it does, it's a bit convoluted, but basically given a validation sample, right? This is the solution or the policy that you obtain by solving, say, this problem. Okay, and I measure the performance of it by testing it for validation data, new data that you've never seen or your model has never seen. Okay, and you take the average over the validation set. It's gonna be your kind of absolute measure, performance measure, right? And in regression, there's an absolute performance measure, which is what? The sum of the squared errors. So this is analogous to SSE, sum of the squared errors in the context of regression. Okay, and now R squared is the best possible way where you assume that you have full information for the data, okay, for the validation set. And RSSAA is based off of sample average approximation, right? You have a solution that is just naively achieved by the traditional SAA, and you evaluate them, well, SSA, like achieved like this, and you evaluate them with the validation data. Then eventually you want to assess the difference between you versus the best possible versus the difference between the rather naive way of finding your solution versus the best possible, and you subtract it from 1, and there's going to be a measure that is kind of in between 0 and 1 is good and 0 is bad, right? So what I'd like you to think about is the connection between what is done in regression in terms of like like evaluating performance of model versus what we can do in estimating like decision errors or like performance in terms of decision errors. Okay? Okay. So wrapping up, so what I've been trying to tell you is, well, optimization and machine learning, right? They coexist in various forms, right? It could be that ML works for optimization like the version that you saw when you optimize, there's ML guide, right? to minimize decision errors, or it could be the other way around, right? It could be that optimization can help ML, right? In a way, for example, what we are doing in lecture 4 is can optimization help machine learning not forget about the ultimate goal of prediction, okay? Don't be too focused on the prediction error. There's something more important, maybe, depending on context. Okay, so they work together. So when they work together, you can finally, I believe, transform your data into smart decisions. I keep saying smart decisions. Now I can say, right, smart decision, what I mean by them is basically robust decisions, stable decisions, reliable decisions, and also interpretable decisions, right? They can be only achievable by like wisely integrating like what is ML and what is optimization, right? And also, if you think about it, something that I didn't cover today is the recent attempt in kind of using optimization to make traditional ML algorithms more interpretable, right? So that's another way of thinking about it. So, well, again, if you didn't follow some of the mathematical contents today, that's okay. What I want you to take away from today's lecture is that there are different perspectives on modeling, right? So it is very important to understand the problem's nature and the structure and even your client philosophy. And there are many modeling techniques that are relevant to different ways of thinking and decision making. And that's it. So we've just gone through many different tools. I feel like I was a bit ambitious in kind of covering, trying to cover as many as possible. But now, if you look at stochastic programming, if you feel like that is relevant to what you're doing, then there's whole kind of huge wide world of stochastic programming itself, right? Robust optimization, DRO, inverse optimization. So I'd like you to just go deeper, go the extra mile, exploring these areas, and yeah, try to keep perspectives when it comes to modeling, right? Okay, so some other interesting topics and works of mine. Inverse optimization, I talked about it, and actually inverse optimization is my main area of research. Okay, so I do a lot of theory of inverse optimization, but also applications. For example, if hospitals are rejecting too many patients and a certain specific class of patients, and I wonder why, right? Why are hospitals rejecting a very specific class of patients? And I try to understand their thinking, their rationale behind the behavior. And what I can do is I can analyze their behaviors, right, quantitatively, try to understand their objective function and try to understand what is missing in what the government offers to the hospitals that is represented in their objective function, right? If I understand that, then what I can do is try to formulate some kind of bi-level programming almost problem where the government decision is to try to give some incentives to add to whatever is missing in the hospital's objective function to really drive hospitals to behave exactly like the government wanted them to behave. Something like this is actually what I'm working on, and specifically in healthcare context. And AI, human interaction and collaboration, again, inverse optimization, right? But inverse optimization can help the central planner that uses AI to better understand the lower level drivers, right? If you think about the Amazon's problem, right? Then when Amazon uses AI algorithms to do the routing, right? We can from time to time intervene the process by updating, right? The human behavior based objective functions or parameters so that AI does not lose sight in terms of how like their agents are thinking, for example, where agents are the drivers, right? And optimizing operations of AI systems in the OR job. So what I'm trying to say is something that I'd like you to think about is like, I think most of you are actually still in kind of OR area. And if you believe in OR, what you can do is, well, there are a bunch of AI devices that are just coming up, right? That are developed by, computer scientists or other disciplines. And it is still our job to optimize their operations, right? For example, if there are a bunch of AI-based diagnostic devices for healthcare, okay, fancy deep learning, high accuracy, but then how do we utilize them, right? We have to utilize them in a very smart way so that you can make sure that those patients who are in need really benefit from this new technology. And there are certain patients who might not actually need this technology. How do we identify such groups of patients, right, that can benefit from AI? Well, that's our job. Okay, I like to think broader. And also there are like fairness issues and ethical risks in healthcare and AI that I am very much interested in. Okay, fair access to care. This is some topic that I've been recently very focused on, and that can be addressed with the help of AI. Okay, think about patients or people who live in a remote area in Korea who have like few hospitals nearby. Okay, how do we help them? They have very limited access to care. Can we actually solve some kind of optimization problem to do some facility location or some logistics to better kind of reach out to them more efficiently? Okay, this type of questions that I'm very much interested in. So if you're interested in any of these topics, you're welcome. All right, just don't hesitate to just reach out to me. Happy to talk with you. Okay, so with that, thank you very much. And the last topic in lecture 4, I've just selected some papers that I find very interesting that are, most of them are around like early 2020. And if you search over this literature, these papers, you will see a number of papers that have already cited these papers recently. That could be a good way of learning the recent literature in this trend. Okay, so any questions? Okay, thank you very much. I hope you enjoyed it. Thanks.